I sort of want to start at a very high level. I mean, you've been at the forefront of the future of general aviation for a very long time. I know you've been studying an awful lot. So, eVTOLs are they the revolution?
Interesting time we live in. I like to think of the current situation in a couple of ways. We've apparently around 150 aircraft development, air vehicle development programs underway around the world, and it's a time in which not only is there a vital need for solving social mobility, society's mobility problems in three dimensions instead of just two, but the convergence of several technologies that make it plausible to imagine having, at first piloted electric vertical and conventional takeoff and landing aircraft as a consequence of not only the gradual advancements in battery electric solutions and some hybrid solutions, and now, of course, the opportunity in the hydrogen space for hydrogen fuel cell electric propulsion added to the mix. So you put all that together, and for my part, I conclude something's going to happen. And so I'm pleased to be around to see all of this develop at a time when we'd imagined some of these kinds of notions 20 and 30 years ago when I was at NASA and working with the industry and the FAA and public-private partnerships called AGATE, Advanced General Aviation Transport Experiments, and then the Small Aircraft Transportation System program. So we it's like the old farmers commercial, not so old. We know a thing or two because we've seen a thing or two. So and to that end, I lived through the after I retired from NASA, I went to work for Ed Yakabuchi and launching Dayjet, the first per seat on-demand air carrier with Clips 500s. The airplane wasn't ready for prime time. The market was there; it was very viable, and the technology was certainly almost ready, but not quite ready in terms of the aircraft. We now have, I believe, an opportunity to finish the work we started back, in the 80s and 90s. It's exciting.
It is now. Uh, the various vertical lift solutions that are being developed right now, most are highly automated. Many are looking towards totally autonomous operation. Are we taking the pilot out of the loop and flying?
My own view is no, not yet. I think that the role of the human changes to a system overseer in ways that, let's talk about it from a piloting standpoint, right? We're pilots, so we're used to heading, speed, and altitude, power, of course, as the means by which we're inside the inner loop of the control of the airplane. When we punch on the autopilot, you could think of that moves us to the outer loop or the strategic part of flying the aircraft, which is where we punch in a destination and a routing, and to first order the aircraft can fly itself. And even with some of the technologies I've seen reported in some of the AOPA materials recently, the idea of auto land is not all that far away in terms that could be practical for general aviation. So I think at least for some number of years, we'll see the role of the pilot slash operator integral to not only the pragmatic issues associated with safety and airspace management, but also the consumer acceptance. We went through at Dayjet back in the early 2000s with consumer behavior modeling and studying customer acceptance of even something as simple as moving from two pilots to one pilot. We chose not to do that back then. in large part because of what our customers were telling us, and quite frankly, the airplane was not quite ready as it is today for that kind of a single pilot operation. So, will we move? You know, from two? We did move from two pilots to one pilot. We can fly single engine. Commercial services these days in Part 135, for example, in various parts of the world. Will we move from one pilot to no pilot? If we did that, my own perception is, and it's not just mine. We're in a community of people who talk a lot together about what the art of the possible might be, is to have a remotely operated vehicle with a pilot, maybe pilot not flying on board, pilot flying in a control station, and they could actually perhaps switch roles, for example. So that's a long answer to your question to say, I think operating aircraft is going to be, for some time anyway, the purview of a human. There are other aspects that need to be thought through as well, including how you manage large numbers of aircraft without relying on voice-based air traffic control, human-centric air traffic control functions, for example.
Well, and I think that's one of the issues that seems to be developing with eVTOLs. I mean, we're going to be putting, if the world goes the way the proponents want it to go, we're going to be putting a lot of flying machines up into the airspace. How do we control all of them? How do we keep the semi-autonomous ones from conflicting with those that are still being piloted by organic computers?
Sure, carbon-based computers, right? Yeah. So you'll remember the efforts that many of us put forth, including with support from AOPA and other of the aviation associations, the program called Next Generation Air Transportation System, under the leadership of initially the Next Gen Office, Joint Planning and Development Office in Washington, D.C., and then later under the leadership of the FAA folks. One of the principles that we wrote, I was part of the team that did kind of some of the founding work of strategic framing of the Next Gen program that led to the congressional legislation. One of the principles that we wrote about in the strategic initiatives package that we delivered for government industry to work from was an idea we called trajectory-based operations. There is work ongoing to move that concept forward in Europe and in the U.S. Over time in programs, in FAA and NASA is helping, of course, and the programs under SASAR, Single European Skies Air Traffic Management Research Program in Europe. This idea, just to boil this down, the trajectory-based operation idea, boil it down to conceivably how a derivative of that concept could make this idea of managing vast numbers of dynamically interacting flight paths safely, with deconfliction and merging, spacing, sequencing, and sort of all of those things that have to happen. If you can represent the flight path in future time based on all the inputs that you can have about the future, that include the atmospherics, include the airspace exclusions, include the traffic flows and things like that. And if you can compute a path that is optimized for fuel or cost or whatever through all of those constraints, then you might be able to, and we believe it's the art of the possible, to have a communication infrastructure between air and ground and air to air that would allow the negotiation of those dynamically interacting paths. It's also a long answer to your short question, but it's an example of a technology that is, I would suggest, close to ready for prime time, or at least certainly exploratory deployments in parts of. I remember how we did ADS-B in Alaska, right? We decided that that would be a great proving ground for the safety benefits of ADS-B. Well, let's think about what a proving ground. In fact, NASA has a program called Grand Challenges which has an idea of proving grounds for having large numbers of these kinds of aircraft interacting dynamically, safely, and efficiently from an airspace standpoint as well as from a vehicle standpoint. There's every reason, in my view, to be forward-leaning about the prospects that we will be able to handle the large numbers of air vehicles in relatively smaller amounts of airspace.
But this then gets into the question of how robust is the technology, and do we, with all the news about various systems being hacked, do we want to have all of these aircraft negotiating among themselves with no human in the loop?
That is the $64 million question, as we used to call it. The prospects for having a cyber-secure operating system, I think, are reasonable to expect. Let me give you an example. I'm also working on the Smart Sky Networks team to deploy the first true broadband, bidirectional, low latency, scalable, low cost, system for air-ground Wi-Fi, basically, in the 4G LTE protocol system. What does that mean? Well, it means that in order for that system to work, you actually have to have a beam-forming technology between the aircraft and the ground antenna. And that means that if you wanted to hack into that, a couple of different things, might need to happen. One of which is, as this airplane is flying past the towers and it's being handed off from tower to tower, beam to beam, right? Every airplane has its own beam. If you wanted to interfere with that, you'd have to have something that could fly and intercept the beam and do something to it before it reaches the airplane. Not in the art of the possible, in my view. And so you have some inherent in these new technologies, such as beamforming for communications, data communications, and connectivity. You have some inherent inhibitors to prosaic hacking, so to speak. The other way, of course, is to be on board with physically interacting with some of the hardware in the aircraft, also plausibly difficult in many respects. So what else might get in the way of being cyber secure? Certainly interfering with the database updates on a machine might be an issue. But if you're using encryption as a means of communicating database updates on an airplane, that's also very difficult to hack in a traditional way. So that is not to say that that cybersecurity is not an issue. Just to say that there are mitigators to many of the prospective ways to do wrong in the space. The outcome has to be that you have something on the order of 10 to the minus ninth level of reliability of communications protocols in this new world of many things flying in smaller amounts of airspace.
Let's move on now to the propulsion systems, and right now the limitation with any kind of electric aircraft is the energy density that's available with the current batteries. Now you're working with hydrogen fuel cells, so tell me how that is going to be, how that's an improvement over a battery system.
The progress that Alaka'i Technologies has made in developing the air mobility solution, really system that they call Skai, S-K-A-I, and folks can go to www.skai.co and read some of the materials about the development of the air vehicle, is based on a long history of hydrogen fuel cells that have been present and proven as durable and reliable in spaceflight operations dating back to the Apollo program, of course, through the Space Shuttle program, and now into the International Space Station. systems that deliver. So what you get, you have some source of hydrogen, you have some source of oxygen, and the two together flow through a device called a fuel cell, which consists of plates of a very thin fabric. Think of for Gore-Tex, for lack of a better example, coated with an also very thin layer of platinum. And the platinum serves in a unique purpose as the hydrogen and the oxygen flow through the cell. The platinum serves to strip the electron off of the hydrogen atom. Hydrogen atom isn't happy being without its electron, but it has to be that way for a little while. And then what's the electron do? Well, that's electricity. So you flow that through the wire, through the motors, you create, power. And then on the backside, the hydrogen is still moving through the membrane, and it's seeking a partner. In this case, an oxygen atom. So two of them pair up with one, and you get H2O, which is, of course, water or water vapor. In the process, you can, I suppose, picture that these separations of electrons, from leaving protons behind in the hydrogen case, for example, is an energy producing process in its own right. And so actually that you get heat out of this process as well. Heat can come in pretty handy if you want to heat a cabin, for example. And in the case of the Skai air vehicle, the tank that's used is storing liquid hydrogen, which is cold, and can be used as a refrigerant for cooling the cabin. It's also used to cool the motors, which get warm in the process. And so it turns out to be a nice, let's call it elegant air vehicle design process that closes around, a speed, a range, and a payload that's pretty impressive.
Now, from the public acceptance standpoint, you say hydrogen, and people think Hindenburg. You say fuel cell, and people think Apollo 13. So,
those are great stories, and they also point to not just progress that's been made, but some of the misunderstandings left behind by those events. Maybe just to take on the hydrogen case with the Hindenburg. It turns out that the Hindenburg skin that you see, all this silver skin, that's a component. It's a paint called thermite, and it's quite flammable. In this case, that thermite skin was ignited in the 1937 films that we still can see on YouTube or whatever. The thermite skin was ignited by a static discharge while the aircraft was landing at Lakehurst, and that began the fire of the skin. And then the fire spread, and of course, eventually the fuel tanks that held the diesel fuel for the diesel motors that propelled the aircraft through the sky, they broke, and the fire you saw pouring down to the ground was diesel fuel burning. What you couldn't see, because it's invisible, if there was flame from the hydrogen, which there likely was, it's escaping upward at 45 miles an hour. And so typically, standard day climb rate for hydrogen, so to speak. And when it burns, it burns invisible to the human eye, and it would have escaped very, very rapidly. So the leave behind from the Hindenburg accident was, oh my God, it's hydrogen. How can that be good? It turns out today that the hydrogen fuel industry standards bodies, and fueling generally industry standards bodies, have built the set of standards for refueling infrastructure, for handling, trucking, producing, that came along much longer after gasoline and kerosene ever had these public standards for safety, and it produced a very, very safe means of producing and handling and transporting hydrogen today. And this is just me hearing things and repeating them, but I've heard from the people who are in that business of producing those standards explain that they view hydrogen as a safer energy carrier than gasoline or kerosene or natural gas or propane and some others. I mean, think about Think about this. I just had this little aha the other day when I was refueling my car at the gas station. I'm reading these health warnings. Don't get it on your skin. Certainly don't get any in your mouth. Things like that. Hydrogen has a pretty significant advantage in being non-toxic to humans and plants and animals and so forth. So it has several advantages from a safety standpoint. Go back to the Apollo story. What happened in that story? You go Google this stuff up, and it's fun to read about it and reflect on it through the lens of all these years since Apollo 13. But the oxygen tank had a stirring device in it that had some wire with Kapton or Teflon coating that the coating had somehow separated or cracked or whatever it did, is the best guess. And when that did that, it created a spark inside the oxygen tank. We know how bad pure oxygen can be from a hazard standpoint with anything nearby in the form of a fire. So that caused that oxygen tank to blow up. So it wasn't there was no hydrogen culpability, let's say, in the Apollo 13 experience. It was the oxygen tank that caused the issue. And of course, just to go back to the reason you even want hydrogen and oxygen in a fuel cell on a spaceship, what do you get? You get electricity, you get water, drinking water, clean water, you get heat, all important things for spaceflight.
Okay, so now hydrogen as a fuel, pound for pound, how does it compare with, say, Jet A? I mean, does a pound of hydrogen give me as much power as a pound of Jet A?
Yes, more so. So let me do the comparisons that I know by heart, and then I'll cheat by looking at my handy dandy graph. Hydrogen as an energy carrier is about 200 times the energy density of lithium-ion batteries. And so that means that for a pound or kilogram of hydrogen, you get 200 times more energy out of it in terms of joules or kilowatts than you do out of an equivalent mass of a battery, for example. But it's also true that the energy density in hydrogen is many multiples of the energy density in jet fuel or auto gas, for example. And so the if this were a race, the winner would be hydrogen.
So I mean, I think from what I've seen so far, as we're looking at the eVTOLs, probably the ones that we are going to see in the near future are going to be hybrids of some sort, usually a turbine driving a generator. But what you're telling me is that the hydrogen-powered one is going to be even more efficient than a hybrid.
More efficient in the conversion, yes, of an energy in a carrier to power. And cleaner from the standpoint of carbon footprint. One of the big advantages, if you can produce your hydrogen out of hydro or solar or wind or probably even nuclear, in comparison to producing petroleum, out of fossil fuels out of fossil-based sources, it's a cleaner carbon footprint than any other fuel source. And it also turns out that in the recycle afterlife of a fuel cell, you get to reuse about 95% of the fuel cell components themselves. It's just like rebuilding an engine, right? You take it apart, take the stack apart. Let me make sure this thing quiets down for us. You take the stack apart and you refresh the plates in the stack with new fabric, and then out of the remaining 5%, you recycle 4.9% of the parts and reuse all of that. And so it's a better than 99% favorable solution for efficiency from that standpoint. Also think of it this way. There's another advantage to the hydrogen solution, which is not lost on those of us who own and operate airplanes, which is sort of what we call the TBO, right? Time between overhaul. The fuel cells, again, proven over a long history in spaceflight, for example, have about a 20,000 hour, quote, TBO, unquote. That's just crazy. I mean, it's so exciting just to think about that for a little bit. And then the motors themselves, electric motors have just incredible durability. And so the prospect of having a very simple vehicle system, very few moving parts, rotors, the fan that blows the hydrogen and ambient air through the fuel cell, the inceptors, as some call them, that the pilot uses to control the vehicle, and the doors. Very few moving parts. So simple is a big part of it. Clean, of course, from the standpoint of recyclability, reusability, and low carbon footprint, and safe. When you have simple as part of your mantra for the development of an air vehicle like Skai, you wind up with a measurable, defensible claim to safety.
But, we've been talking about hydrogen as a transportation fuel for at least 40 years, and yet it still hasn't come to fruition. Why not?
Well, I think part of the story, in the case of Alaka'i Technologies, and Brian Morrison, the co-founder of the company, it was a time about 7 years ago, when he called and said, "Hey, Bruce, I'm thinking about an electric," he called it e-copter at the time, e-copter, and I need to know what the demand profile is for transportation that an air vehicle like that could satisfy. So I have another company called Air Markets Corporation that does demand modeling for problems like this, using agent-based models to represent the behavior of humans making decisions. It's a consumer modeling, choice modeling tool. And so we gave him some data that showed the range and the uptake in the market at different prices for different speeds and different payloads of vehicle sizes. So he had this sweet spot that he was trying to design a vehicle to fit into, and he was working batteries really hard, working with the best information he could get about the future of battery energy density. And he could not close a vehicle design around that big sweet spot of about 100, at least 100 miles an hour. More can be better, with a 1,000-pound payload and about 4 hours of endurance. Tried for a few years to make that work. Didn't work. Ran into, serendipitously, some folks in the hydrogen world. Got in touch with some folks who build hydrogen fuel cells and asked the question, can you build a flight weight hydrogen fuel cell? Because traditional ones are built for, traditional fuel cells are built for like ground tugs and forklifts, where you want weight. You want it to be really heavy, so you're not playing any weight minimization game there. But when he asked, he got an answer from one of the companies that said, we're in. This is going to be a big deal, and we can make a flight weight hydrogen fuel cell for you, which they are now doing. And so it reduced the weight of the hydrogen fuel cell sufficiently to allow the closing of an aircraft design around a speed of in excess of 115 or so miles an hour, payload up to 1,000 pounds, and an endurance of up to 4 hours, in a vehicle that weighs about 4,000 pounds in the early versions of it. And of course, over time, we'll figure out how to get weight even down further. And the rest of the answer to your question, I think, about why haven't we looked at this before, was there hadn't been a team quite like the one that I know at Alaka'i Technologies, that included not only an inventor who was unwilling to let go of the problem. But some other folks in the team who I'd been working with back in the NASA AGATE days, public-private partnership, they were in the private sector. I was working at NASA, and we worked together to develop the industry design guidelines and systems and standards for systems and architectures and means of compliance for glass cockpits, for composite material systems, for data bus and database systems, for single lever power control. All of these technology we sort of take for granted today came out of those that work together between the FAA, NASA, and industry in the 90s and early 2000s. So I knew these fellas, from having worked with them before. I knew they were a team that could, if anybody pull this together. What they were lacking was an investor who had a capacity for this kind of vision. Brian found such an investor, and so you put all that together, and you put together a commitment to the sustainability of the future of an aviation solution like this. And I don't know that that's a unique formula, but it certainly is one that worked here.
Just how complicated will be creating the infrastructure for hydrogen?
At first, it will be satisfactory in small numbers to use truck carrying hydrogen to points of operation. In the longer term, what you'd like to do is have an in situ capacity for producing hydrogen on site and storing it for those kinds of operations. The hydrogen companies that we're working with, hydrogen production companies, are working with us to think all of that through. We're also, we in this case, the folks with Alaka'i, are in conversation with a couple of states who envision themselves being leaders in the development of hydrogen economies and hydrogen society. There are several countries around the world, about 6 at last count, who are all in on transitioning from the current power systems to hydrogen economies. And so that movement is on, and it's got a ways to go, of course, before it reaches a hydrogen fueling station near you and me. But the movement is underway. California just announced, well, actually they've been at it for some time, but they have somewhere in the neighborhood of 100 hydrogen fueling stations for the people in California who own hydrogen fuel cell cars. And the state announced a plan to double the number of fueling stations for hydrogen cars. So the moving parts are certainly in existence for building out infrastructure, including the role that states might play and governments at the state and local level.
So put on your or pull out your crystal ball. Realistically,
when you look,
when will hydrogen fueled aircraft be in common usage? How far out are we before we actually see this?
Common usage is some years away. No question about that. It'll start in isolated pockets, at first, and also it'll start before it's common in the sense that it's available to the quote public. It'll very likely start with specialized missions like emergency management services and disaster relief aircraft operated by, state or federal agencies, public safety organizations of various kinds, Coast Guard, National Guard, so forth. And so we'll have an early start, we believe, in that form. When we have a defined market and a partner to work with who see the value that we see in the hydrogen solution, and an operator partner who is willing to go all in the deployment of a service, a transportation service in that kind of a market. That will be an example of a pocket, whether that's a city in the U.S. or a city somewhere else in the world, is still yet to be determined. And you asked about how long will it be. If you just kind of play the timeline of, I'm used to thinking of the behavior of innovation life cycles as an S curve, right? Starts out slow, and then it builds up momentum, and then when it saturates the market, it begins to mature. That startup phase in any innovation life cycle of a major system like what we're talking about here is going to be, hopefully not double-digit years, certainly more than a few single-digit years. If I were trying to put a marker on the crap table, I'd probably put it somewhere around 4 or 5 years. Well, think about it this way. What has to be done? You have to certify the air vehicle. And if you look at the certification timelines for aircraft and decompose the certification steps through the lens of the number of moving parts on the vehicle, and you can then do the math on how many vehicles you have to have and how many hours a year they have to fly to gather all the data for the certification process. And you look at the Skai air vehicle, air mobility system, and count the number of moving parts and just say, wow, okay, so that means, maybe I need a fewer number of conforming prototypes. Maybe I only need to fly them for, less than 24 months, let's say, to gather all the data necessary to satisfy the regulator. So that's one thing that has to happen. The build out of the infrastructure is the second thing that has to happen, of course, starting with trucking of liquid hydrogen for this purpose. You can operate the vehicle in today's airspace. In my more fun flying, I fly a seaplane, and for me, it's a lot like how I imagine these eVTOLs will be operating at low altitudes in the Class G airspace mostly. And so you can do that today. Could you do it better if you have larger numbers, if you have a connectivity solution, radios that make vehicle to vehicle, vehicle to infrastructure, vehicle to cloud, communications possible? Absolutely, no question. And that's coming as well. And so the pieces of the puzzle that have to be solved, including, by the way, pilot training and maintenance facilities and training maintenance people, each one of those cycles, and many of them can be done in parallel, of course, requires an investment. And so when you lay that out over a timeline of, maybe 5 years, it seems plausible.
Although talking about certification, when you're looking at a highly automated vehicle, at this point, the FAA is running pretty gun shy after the 737 MAX situation. So it looks like it's going to be much harder to get automated systems through them.
Well, I think in this case, the folks we're working with in the FAA are very much supportive of the timeline that we're trying to work on. They understand, the lessons from the 737 MAX. The nature of that aircraft and its issues is certainly leaving a bit of a shadow, casting a bit of a shadow on all of us who would see more automation as a better thing. And so in the process, we'll have a vehicle that is not going to rely exclusively on automation. It will be capable of being, let me say, hand-flown with the support of an autopilot, such as we take for granted today in our general aviation aircraft. And so I don't see that as an inhibitor at the beginning. Where it becomes, a challenge will be when we want to start moving the pilot from being an integral part of speed, heading, and altitude and power into an observer of the system, right? That is taking care of itself. That's where we really need to prove what the levels of durability, reliability are for these systems.
Just curious, do you see the Uber model as being what the world will be, where you use an app, you call up your eVTOL, and you get You know, you pick it up at some sort of port downtown, flies you to wherever you're going, and then maybe you to another port, and then maybe another ground transportation for the last mile. Is that where we're going to be?
That's a good model, I believe. And let me tell you our view of it. There needs to be a very highly integrated. Excuse me, just a minute. There needs to be a very highly integrated, let's call it a backplane, to that ride-sharing app on your mobile device, on your phone. And what I mean by that is that that backplane needs to provide real-time access to all of the data necessary for a three-dimensional solution for flight path with pricing, with variabilities accounted for and uncertainties in airspace, in atmospherics, winds and weather, with traffic flows and things like that. All of that needs to feed that app on your mobile device in order to give you a price for your trip, much the same as Uber and Lyft apps do today. And they actually give you some choices too, right? You want Uber Black, you want Uber X, you want Uber Pool. All of those are great sort of leading precedents for how consumers can expect to interact to gain access to a ride. And the backplane work you could think of in many respects as a kind of an operating system for air mobility. And so some of us in the industry are involved in thinking through all the software development necessary and integration necessary to create a system like that. At Smart Sky Networks, they've invested in the development of what's called an aviation data marketplace called Sky Intelligence. And there are several certain data marketplaces in aviation now that has started to bubble up around the world. And what they do is they create a means of aggregating data services, algorithm services, security services, commercial services in an open what's called an open system architecture that allows an app developer like an Uber in this case, or one for Alaka'i or the Skai or vehicle, to come in and draw from the various sources and options for data and algorithms, and makes it simple by giving the developers, API interface to all of those sources of data and algorithms, and produce their solution for the customer on the mobile device that then says, hey, I'm here, I want to go there. And the rest of the story will be how clever can you be in showing somebody in 3 dimensions on your mobile device what that path is going to look like that we take for granted on a Google map today in 2 dimensions.
Well, fascinating. Well, it's a brave new world, Bruce.
It certainly is. Who would have imagined? It's hard to picture this even 5 years ago. It's been propelled by fundamental changes in technologies that did not have to come from the aviation world, right? Electric motors, the hydrogen fuel cell story, much of the autonomy and automation technologies, and the emergence of the drone world, right? And everything that enterprise brought forth as pieces of the potential solution sets. This is really, well, I could go on and on, the car manufacturing technologies and so on. So it is a brave new world.
Well, thanks for taking the time to talk about this and explain all of it, and keep us up to date on what Alaka'i is doing, because we'd certainly like to do some more reporting on that.
Absolutely. We look forward to the time when we can invite you up to the test site, and you can watch this magnificent machine do its work.